Hi, this video contains the notes for section 2.3, which in our book is titled Limits at Infinity, also known as the end behavior of functions. And you've talked about that in other classes, so we'll see how we reference our knowledge of functions and how we change a little bit maybe the language that we use to talk about end behavior. So let's start by looking at some functions that we know. Let's consider the function 1 over x. This is a pretty important function in analysis, in calculus, and I would expect that you have an idea what that looks like. If you don't, I'd like you to pause here for a second and think about that graph, and without your calculator, try to come up with a sketch for that graph. Okay, so you should have a graph that looks something like this. That's the point 1, 1. It also goes through the point -1, -1. This is a real important kind of relationship, this inverse relationship in physics, also in chemistry and other sciences. And sometimes we just, when we're talking about the physical sciences, and negative numbers don't have any meaning. We just look at it in the first quadrant. But here we're interested in both. So let's, what can we say about this function? What different things can we use the language of limits to, how can we describe some things here? We could say from the last section, we could say that the limit as x approaches 0 from the positive side. So as x approaches 0 from the positive side, what's happening to our function? Our 1 over x? Well, as you get closer and closer to 0 from the positive side, this gets bigger and bigger and bigger and bigger. The x gets smaller and smaller, and the quotient gets bigger and bigger, right? 1 divided by some tiny, tiny positive number. So we would say that's infinity, and we can confirm that. We're looking at the graph. You can see how this shoots up here and grows without bound as we get closer and closer to 0. Of course, you can't just plug in the 0. You get 1 over 0, but 1 over 0 means to us infinity. Now, if we approach from the other side, we get 1 over a tiny negative number, and we would call that negative infinity. And likewise, we can see in the graph how it's plummeting down to negative infinity there. And since these are different on either side, we would have to say that the limit as x approaches 0 without any qualifier about what side. Since the two sides were different, that means we would have to report that that limit does not exist. Right? But what about this? Could we ask this question? What's the limit as x approaches infinity of 1 over x? In other words, what is this function doing as x goes off to infinity? Well, it looks like as x goes off to infinity, it's getting closer and closer to the x-axis. And in fact, we could say that it has a horizontal asymptote here. And we would say that as x gets bigger and bigger, 1 over infinity gets closer and closer to 0. Right? It's approaching this horizontal asymptote. And how about, what's the limit as x approaches negative infinity? 1 over x. Well, here it's approaching from underneath, but it's approaching that same asymptote. Now, don't make any mistake here. This is not a two-sided limit. You know, approaching infinity over here and approaching negative infinity, those aren't two sides of the same thing. Those are two very different directions. So if these happen to be different things, there wouldn't be any consequence in the same way that when these are two different things, we have to report that it doesn't exist. That's the same, does not apply here. All right, so there's your first couple of limits. We maybe understand now why this is called a limit at infinity. It's about what happens when x goes to infinity. Here's another quick example. There's the function x cubed minus x. Again, I would expect that you could come up with a graph of that without your calculator, without too much work. So I want you to pause and try to do that. Maybe you tried to factor this to get your graph. If you did, you find that it has zeros at -1, 0, and 1, right? After you factor out an x and then factor the x squared minus 1. So, and you know it's a cubic function, it's positive in front, so without really plugging in any numbers, I think you should you could conclude that it must look something like this, right? It's a cubic function, and it's not an upside down cubic function because there's not a negative in front of the highest power. These are things that you learned for the first time in Algebra 2. All right, something like that. Now let's see, we could ask, what is the limit as x approaches infinity of this function? I could call it f of x, or I could write out x cubed minus x in here, same thing. Well, as x approaches infinity, this just looks like it's blowing up. So that's just going off to infinity. And if we go the other direction, it looks like it's plunging down to negative infinity. So in a way, I think it's not as interesting as what happened here. Here we actually got an answer, a numerical answer. It's approaching 0. Right? It's more interesting when something approaches infinity and you get a number. Here something is approaching infinity and you're getting infinity. Not really quite as interesting. So this is a way, you've seen this before. You've talked about things like this. You've talked about end behavior in probably Algebra 2 and maybe a little bit in pre-calculus. So this is just a fancy way with our new limit notation of saying something that you already knew how to say. You already knew how to say, well, the end behavior of this function approaches infinity. It goes up to positive infinity. And you know that since this is an odd degree, the arms go in different directions and all that kind of thing. We're just saying that with different notation now. All right, here's a couple more interesting functions. How about the tangent inverse function? There are quite a few functions that you should be familiar with. And what I mean by that is you should be relatively comfortable plugging a few numbers into them, and you should have an idea what the graphs of those functions look like. And this would be one of those. I expect that you might be a little bit less familiar with this one, but it's a good one to familiarize yourself with, or familiarize yourself with. So if you want, you can pause, see if you can come up with a graph of that. Now, you might think about it this way. What is the tangent inverse function? What is any inverse function? Well, maybe you're more familiar with the tangent function, right? So if you're working with the tangent function, of course, this must be an angle, right? And since we're in calculus, we would measure those angles in radians, so you might think about plugging in some of those nice, quote-unquote, nice numbers from the unit circle. And sorry to keep asking you to pause, but if you're, why don't you pause here and try to fill in these values, again, without using your calculator. All right, since tangent is sine over cosine, the tangent of 0 radians would be 0. This would be the square root of 3 over 3. This would be 1. This is the square root of 3. And when you try to do pi over 2, when you do this sine over cosine, the cosine of pi over 2 is 0. So you get does not exist. It seems like it's trying to go to positive infinity there. Right? It's a positive 1 on the top. And as you sneak up pi over 2, as long as you're approaching it from underneath, then it seems like it's trying to be positive infinity. Right? Now, what is the effect of inverting a function? What does it mean to have the inverse of a function? It means take all the x's and the y's and switch them. And if you do that, what you're going to find is you should get a graph that looks like this. I didn't include the negative values here, but you can figure those out. You can pause and think about that for a minute. Try to make sense of that graph. Where are these horizontal asymptotes? Well, it looks like as if we switch the x and the y here, if we make these the x's and these the y's, it looks like as x goes to positive infinity, the y values get closer and closer to pi over 2. So this is at pi over 2, and this is at negative pi over 2. If you're more familiar with the graph of the tangent function and its little pieces that go like this, right? The graph of the tangent function, y equals, another one of course you should be familiar with, looks like this is just a really rough sketch of it. It looks like this, right? Well, what happened to all these other pieces when we inverted it? Well, since we want the inverse of the tangent function to be a function, so we just picked the middle one and inverted that. The other ones would stack up, right? And that would mean this wouldn't be a function. It wouldn't pass the vertical line test. So what you have here is the inverted middle piece here. And of course, when you switch y's and x's, these vertical asymptotes become horizontal asymptotes. All right, so here's a little review of what those functions look like. So see if you can answer these questions now. What's the limit as x approaches infinity of tangent inverse x? What's the limit as x approaches negative infinity of tangent inverse x? Before I write the answers in, pause and think about that if you don't have it already. Well, this would be as x approaches infinity, that's pi over 2, and as x approaches negative infinity, it's getting closer and closer to negative pi over 2. So there's an interesting function with horizontal asymptotes. And one more. How about this one? I'm not going to go into, I could make a whole video about this function, but this is like taking $1 and investing it in a bank and compounding it with a 100% interest rate and compounding this many times. You talked about that when you worked last year with formulas for compound interest and then eventually interest compounded continuously. And you can graph that on your calculator if you want. That's a little bit harder to graph by hand, and I wouldn't necessarily expect you to be familiar with what that graph looks like. But you should know this. This is an important function later on, that the limit as x approaches infinity of this function, that's e. The full justification for this is not possible until we know some more calculus. But certainly if you just plug numbers into this and plug bigger and bigger numbers in, you see that it's approaching this number e, which we should know is approximately 2.71828, and goes on forever without repeating like pi does, right? Also, the limit as x approaches negative infinity of f of x is also e. And there's a graph of this in your book, or you could graph it with your calculator and see what that looks like. But that's a good one to recognize comes up every once in a while, and we'll discuss that more later on. So there are some functions, some of which you've seen before, and maybe that's a little bit less familiar, and some of the things we can say about them as x approaches infinity. Now, one of the common types of functions that you have to work with in this context are rational functions. So, look at a couple examples, and then we'll try to generalize how to deal with them. What is the limit as x approaches infinity of 2x squared minus 1 over x squared plus 2x minus 3? Your algebra instincts might tell you that you should try to factor these things, and indeed I think the bottom one would factor. The top one doesn't really factor in any meaningful way. And although you can factor the bottom, it's not going to do anything particularly useful for us. So instead, let's think about what happens as x approaches infinity and see if we can evaluate this limit. Imagine plugging a very large number into these expressions. Like, say, how about 1,000? That's not that large, but big-ish. Well, what's 1,000 squared? 1,000 squared is 1,000,000, and so this would be 2,000,000 minus 1. So on the top here, if we plug in x equals 1,000, we would get 2,000,000 minus 1 over here, 1,000 squared, that would be 1,000,000 plus 2,000 minus 3. Now, it should be pretty clear that this minus 1 really doesn't make much of an impact on 2,000,000. So 2,000,000 minus 1, sure, it's 1,999,999, but that's close enough to 2,000,000. It's hardly different from that. Here, this might seem like a bigger change, right? That changes that here, right? 2,000 and then the minus 3. That's kind of like the minus 1. Doesn't make much of a difference. But I hope that you might appreciate that as we plug in bigger numbers, like let's say we try plugging in 1,000,000 now. That would be 10 to the 6th. Well, that would give me 2 times 10 to the 12th, or in other words, 2 trillion minus 1 over 1,000,000,000,000. That's 1 with 12 zeros after it, plus 2 times 10 to the 6th, 2,000,000 minus 3. And maybe you can appreciate that what just happened is, although this is like we're adding 2,000,000, that's a lot, right? But actually, it's less significant than this was. Because if you look at this trillion here, this is now making a difference 6 decimal places in from the front of this number. The difference between this and this is kind of a gauge of how much of an impact this number has. So on the top, we're going to have something that's really close to 2 trillion. And on the bottom, we're actually going to have something that's really close to 1 trillion. Because this only made a difference 6 decimal places in, right? If you wanted to write down what's a trillion plus the 2,000,000, when you line them up like this, all of a sudden the 2,000,000 doesn't look so big anymore. And you can think about the kind of budget negotiations that go on in our capital these days. When if somebody were arguing about how to reduce the deficit, which is measured in trillions, and they said, I've got this great idea, it's going to save us $2 million, they'd be laughed out of the room because $2 million does not even make a dent. You'd have to have an awful lot of plans, I guess 500,000 of them, to save $2 million before you're going to make any kind of dent. All right, so what's the point of all that? The point of all that is what really matters when you look at these limits of rational functions is what is happening with the highest exponents. And in this case, all of these things that are not the highest exponents, they do not matter. This is the highest exponent, this is the highest exponent. So what's the limit? It's the coefficients of these. It's 2x squared over 1x squared. All lower exponents do not matter, so that gives us a limit of 2. A couple more quick examples of that. What would the limit as x approaches infinity of 7 minus 5x cubed over 3x cubed minus 2x plus 1? What would that be? Well, by the same reasoning here, the only thing that matters is the highest exponent. The highest exponent is x cubed. I've got one of those here, and I've got one of those here. Nothing else matters. So what's the limit? Since these are the same top and bottom, and they're both going to be going to like million, trillion, and bigger numbers together, right? This will always be the same very large number. Then the coefficients tell me what that limit should be. And notice that that minus sign is attached to that term, right? 5/3 would be incorrect. Now, what if the highest exponent on the top and the bottom does not match up? What then? Well, what about this? Of course, this would be an example of that, right? And we know that that's 0. So here, what's happening is, if the biggest exponent is on the bottom, then that's going to drive our limit down to 0. That's a simple example of that, but it works in any case. X plus 3 over 2x squared plus 3x minus 1, that would be 0, because where's the highest exponent? Here, and it's not matched on the top. That means this is going to blow up faster than the top, which will drive it down to 0. What if the highest exponent is on the top? Well, we looked at the function x cubed minus x earlier. I could make it like that, right? And so there's the highest exponent. It's not matched there, so that goes to infinity. How about the limit as x approaches infinity of 5x to the 7th over 1000x to the 6th minus 17? What about that? Well, where's the highest exponent? It's on the top. So even though this has 1,000 in front of it, because x is going to blow up to infinity, this ultimately is going to fade compared to this. This is going to grow so much faster. There's that little 1,000 in front of it. That's hardly going to matter when you're plugging in numbers like a quadrillion, a quintillion, 1 with 100 zeros after it. And there's no bound to the numbers we're going to be plugging in here. So that will come to dominate since the highest exponent is on the top. Means we're going to infinity. If the exponent is odd and you're going to negative infinity, just be careful to check your signs. Like, for example, what's the limit as x approaches negative infinity of 3x cubed over 2x squared? Highest exponent is on the top, but since we're plugging in negative infinity and negative numbers cubed are negative again, that's going to go to negative infinity. Right, so just watch out when you have a negative there. And last, actually a couple more quick things. Let me give you an example which I really consider to be the same type of problem that we were just doing. What about something like this? Where's the highest power? Well, you might look and say, oh, the highest power is on the top. But actually, since this is under a square root sign, the highest power on the top, that's really like the square root of 5 times the square root of x squared is x. And then on the bottom, that's like 2x. Right? So because it's under a square root sign, all exponents that show up under here, it's really like they're cut in half. Notice that I knew the -7 wasn't going to make any difference, likewise the +1. So now that I've looked at it like that, that would be the square root of 5 over 2. The coefficient of this is the square root of 5, and they really are the same exponent, top and bottom. Likewise, we could make up all sorts of crazy problems like this. It don't come up very often, but we need to know what to do. How about the cube root of 7x to the 6th minus x squared plus 5 over the square root of 4x to the 4th plus x. Well, the highest exponent here, on the top, we've got, that'd be the cube root of 7, and then the cube root of x to the 6th, that's like x to the 6/3, or x squared. And then on the bottom, I've got the square root of 4, the square root of x to the 4th is x squared. So even though it didn't look like it right off the bat, those are actually the same power, top and bottom. So the answer would be square root of 4 is 2. All right, so watch out for those. And then very last, just a couple more functions that you should be familiar with. The exponential function. There are lots of exponential functions out there, but the one that we call the exponential function is e to the x. It looks like this and it blows up like that. It's the one that we use to model things like populations of bacteria growing, or your money growing in a bank account when interest is compounded continuously, and so on, right, by the PERT formula. Very important function. And the inverse of that is the logarithmic function. The logarithmic function. If I'm talking about logarithms and I don't specify the base, that means we're talking about the logarithmic function, which means natural log. And however you want to think about this, you want to think about inverses are reflections over that line y equals x. Those are the inverses of each other, right? Exponentiation is undone by logarithms and vice versa. All right, so anything interesting we can say about limits here? It would appear this is just blowing up to infinity. It appears the interesting thing we could say here is happening at this end. We could say the limit as x approaches negative infinity of e to the x is 0. And in this one, it would appear that we could say, this looks like this is the interesting thing that's happening. This is flattening out, but it never actually hits an asymptote. It will grow tragically slowly, but any bar that you set, it will eventually get crossed. Maybe that's worth saying too. Even though it looks like it might have a horizontal asymptote, the limit as x approaches infinity of the natural log function is infinity. And here, the limit as x approaches 0, we have to say from the positive side because it doesn't exist over here. Can't take logarithms of negative numbers. Oops. Of the natural log function is negative infinity. Plunges down like that, has a vertical asymptote there. May be worth saying very quickly, I promise this is the last thing, that related to this graph, we could also talk about what does the graph of e to the negative x look like. What's the effect of swapping a negative x out for an x in a function? Maybe just pause for 1 second and see if you can figure out how that affects that graph. Right? What it does is it flips it like a y-axis, symmetric to y-axis kind of flip. So now, with this graph, the limit as x approaches infinity of e to the negative x, that's equal to 0. That should make sense, right? Because e to the negative x is the same as 1 over e to the x, right? Isn't that what negative exponents do? They flip things over. And if you plug infinity into this, this is 1 over something that's blowing up, and we know that, just like 1 over x, that's going to be 0. All right, that's a whole bunch of stuff. In class, you'll have a chance to practice some of those concepts with some problems.